Okay, the last situation we looked at, I believe, was the example of a rigid oscillator here in purple. And I didn't have that labeled, didn't have that in purple before, but this thing's oscillating, and we've got two strings that are attached to a bungee cord at the wall. And one of the strings, the way this thing is angled, is 7 meters longer than the other. So that, and that's indicated. I had a right angle drawn here, just out of habit or something, without thought. I put that down, inserted, that made the distances equal, which is ridiculous. So these angles are equal, so these distances here are equal, and then you have an additional 7 meters here. So that any wave disturbance that propagates as a result of the oscillation here is going to have 7 meters further to go on this string than it does on this. Now we're given the tension and the mass per unit length in the strings, they're identical. And from that we calculate the propagation velocity. And that's a very straightforward calculation that I don't think anybody needs any help with. So I got 17.5 meters per second. As always, check my figures. It's probably off by a couple of hundredths, but I think it's probably pretty accurate. And of course I've got egg in my face if it's way off. Okay, if that's wrong, you can fix it. And you can fix anything that follows from it. Okay, now if we want to get maximum motion at the bungee cord, we want peaks of the wave in one string to meet peaks in the other. If we want minimum disturbance of the bungee cord, we want peaks in one to meet valleys in the other so that they cancel out. Now, how's that going to happen? Well, I'm going to say that peaks meet up, and I don't know what happened. Peaks meet peaks. Okay, peaks meet peaks to get maximum motion. I already said that. I want to make sure I had the words there. Hope you can read that. Okay, so when's that going to happen? Well, a peak is going to be produced here at the same instant it's produced here, because this oscillator, it only goes to the maximum positive displacement once per cycle, and it's going to do that simultaneously with both, the oscillator being rigid. So that if the wavelength is 7 meters and there's a peak here, then you go through the full wave and you're at a peak here. Since you're also at a peak here, you have peaks together here, and now they have equal distances to travel at equal velocities, and peaks are going to meet peaks. So wavelength of 7 meters will cause peaks to meet peaks. It'll cause maximum motion in the oscillator. Now, if you have two complete waves, so you go from peak to valley to peak, one, peak to valley to peak, another, then when you have a peak here, you're going to have a peak here. And when you have a peak here, you have a peak here, so peaks are meeting. Peaks are going to be together at this point. In other words, when you have a peak here, you have one here, and now those peaks travel equal distances, and the same thing happens. The same thing happens if you have 3 peaks. So that the wavelength, if you have 2 peaks in the 7 meters, is 7 meters over 2. If you have 3 peaks, 7 meters over 3. So that's the series of wavelengths that will lead to maximum displacement at the bungee cord. Okay, looks like a hook, but that's a hook in the end of a very short bungee cord. Okay, now minimum motion is going to happen when peaks meet valleys. How's that going to happen? Well, if this distance is half a wavelength, then you have a peak up here, and you go to, you cross equilibrium, and you go to a valley here before you cross equilibrium and come back to another peak over here, which means that you're going to have a valley here when you have a peak here. You have a peak here when you have a peak here. So if you have a peak here, you've got a valley here. So now you have a peak and a valley going together down the line, and you get cancellation. Peaks meet valleys, minimum disturbance of the bungee cord. Okay, that happens if you have the 7 meters is half a wavelength. Now, if you have 1.5 wavelengths between here and here, you can figure out, and you should be able to visualize why you're going to have a valley here. At the same time, you have a peak over here. And if you have a peak here, you have a peak here. So this peak is meeting a valley. They go equal distances, peaks meet valleys, and minimum motion. If you have 2.5 or 5 halves of wavelength in the 7 meters, same thing. Okay? If you got 2.5 wavelengths, you're going to have a valley here when you have a peak here. So this valley will meet a peak here, and they'll go together down here. So there's your sequence, and these are very obvious sequences. It's going to be half a wavelength, 1.5, 2.5, or 1/2, 3 halves, 5 halves. Go on to 7 halves, 9 halves, etc. As far as you want to go. Okay, well, then you want the frequency. Well, the frequency is really easy. Okay, usually in these geometric situations, it's easy to find the wavelength that you want. Having found the wavelength, if you know the propagation velocity, then it's just a straightforward matter to find the frequency. If you don't write this relationship upside down, as I did without thinking, then I started to calculate and realized the units weren't going to be right, and the whole idea wasn't going to be right. I was going to get a fraction of a hertz here when I need more than a hertz, because the distance the wave travels in a second is greater than its maximum wavelength that we get from any of these. So anyhow, for example now, to get the frequency for the 7 meter wavelength, we divide the propagation velocity, 7.5 meters per second, by the 7 meter wavelength. We get 2.5 hertz. We could then divide by 7 meters over 2. Probably easier to realize, well, if you got half the wavelength, you're going to be divided by half as big a number. You're going to get twice the result. You're going to have 5 hertz. Or you're going to have 7.5 hertz when you got 3 wavelengths. And you can do similar calculations here, and you can observe similar patterns in the results in the sequence of frequencies. And that might relate you to all the formulas you see in your book that nobody in their right mind ever remembers, unless they have a really good memory for formulas. A bunch of confusing formulas for situations that could be analyzed in a much simpler manner. Now, this doesn't mean that you shouldn't be able to derive those formulas, so I'm going to take just a second to do those, just as kind of a little extra here. What's this? Okay, you're going to have maximum motion of the peaks if lambda is 7 over n times your 7 meters. So (7 meters over n), which implies that your frequency is going to be what? It's going to be n times your 17.5 meters per second divided by 7 meters, which is going to be n times 2.5 hertz. Okay, so you should be able to formulate that, having solved it, formulate it in mathematical terms. And you can do something very similar down here. Okay, it's going to be, well, your wavelengths are going to be 2 times 7 meters, 2/3, 2/5, and so forth. You symbolize that. Your odd numbers can be represented by 2n minus 1. So if n equals 1, you get 1. If n equals 2, you get 3, etc. Easier to formulate these things than to remember a bunch of formulas, unless, of course, you have the skill to do both and the ability to see within the formula exactly what's going on in the system.